lesson, we're going to be talking extensively about free body diagrams and writing net force equations. In this unit, dynamics unit, forces unit, this is the most important step in solving for whatever your force problem is. If you can draw a free body diagram and write the net force equation, then you're going to have a much simpler time solving for your problems. Okay, so to illustrate this, we're just going to start really basic. Really the first goal is, can you draw a free body diagram? And a free body diagram is just anything, it's just a picture that shows all of the forces involved. Okay, so right now I've just got a box at rest, and we want to draw all of the forces that are present. Well, we have our weight force, and we have our normal force. Okay, it's at rest. There's no other forces acting on it, just gravity pulling it downwards, and then the surface pushing up on it. That's what the normal force is. Okay, one key idea along as you draw these free body diagrams, it's always a good idea to, if you know the equation of that vector, like we know that the weight is the mass times the gravity, that's always important, is just being able to write an equation to go along with your vector. Okay. Well, according to Newton's third law, these forces would be equal and opposite, so our normal force would also equal the mass times gravity. Well, let's take it up a notch. Let's say that this box was being pulled with a force of 10 newtons. Let's also say that there's a friction force of 5 newtons. How would we figure out what the net force would be? Well, it'd be really simple. We're just going to do 10 newtons minus 5 newtons. That would be our net force equation. We're going to take this positive vector and subtract it, because these vectors are going in opposite directions, and voila, we came up with our equation. We can solve for the net force. Okay, and most students, they understand this because you see the numbers and it makes sense. So our net force here would be 5 newtons. Let's take this though, and instead of using numbers, because with most advanced physics type problems, they don't always give you numbers. They want to know, can you solve it algebraically? So let's take the same box that has weight, it has the normal force, but let's say that we have some sort of push force, so I'm just going to label that F sub P, and some friction force. How are we going to write a net force equation for this block? Well, it's going to be the same thing that we did up here. If we know that this box is going to accelerate to the right, meaning the push force was greater than the friction force, we know that these vectors are not balanced. There is an unbalanced force, and we can write an equation. So just like up here, we did 10 minus 5. Well, what we're going to do here is FP minus FF. There's our net force equation. Okay, so being able to put it in symbol form can be difficult, but if you can do it with numbers, you can do it with letters as well. All right. And what would this equal? Well, according to the Newton's second law, F equals ma. So our FP minus our FF is going to equal the mass times the acceleration. And so this is important because in a lot of the forces problems that you might have, they might ask you to solve for the acceleration. Okay, and so to solve for the acceleration, we just have to divide by the mass on both sides. So our acceleration equation would be Fp minus the friction force divided by the mass. Okay, sound good? Let's do one more problem. Let's kind of kick it up another notch. Very typical problem here. Block on an incline with angle theta. Here we have our block. Alright, and we want to know what would be the net force equation. Okay, let's assume friction again. So let's draw our free body diagram. Our weight, our gravity will always come downwards. That's equal to the mass times gravity. And our normal force always perpendicular to the surface. Okay, so here's our surface, perpendicular, got our normal force. Okay, now whenever you're drawing these free body diagrams and you have an angled vector, meaning an angle to in relative to the block itself. So here we have our block. Our x and y axis is going to be represented by these dotted lines. Okay, so relative to this xy coordinate, we have an angled vector, which is our gravitational vector. We need to break this vector into its x and y components. So let's go ahead and do that. We're going to have a downward vector, so we're basically resolving this vector into its x and y components. And so when we do that, we are essentially getting rid of this downward vector and just taking into consideration the two new vectors that were drawn from it. And when this also happens, when we have this on a block on an incline, it just so happens that this angle theta always gets put in between our gravitational vector and our y-axis vector. So our angle theta will go right there. Now, just like we came up with an equation for our weight, which is the mass times gravity, we need to come up with the equations for these two vectors as well. Okay? Since the weight is our force and we have an angle, this vector is adjacent to this angle. So this vector right here, its equation is going to be mg cosine theta. This vector right here could also be placed right here. So that would be opposite of our angle theta. So this vector right here, mg sine of theta. Okay, and we also said that we are going to assume some frictional force. So the question is, how are we going to write a net force equation for this block? Well, according to Newton's third law, this normal force and this mg cosine theta, they are going to be equal and opposite to one another. So we're left with mg sine theta and the frictional force. So our net force equation is going to equal mg sine theta minus the frictional force is going to equal the mass times the acceleration. If we wanted to solve for the acceleration, we once again would just put that net force equation on top, mg sine theta minus ff, and divide by the mass. Okay, so hopefully this video is helpful for you in A, drawing the free body diagrams, and B, writing a net force equation, particularly just using the labels and the symbols of the vectors. Thanks for tuning in.